Yes, let's move on to the eighth problem, which says that using differentiation in time domain and differentiation in frequency domain properties, find the Fourier transform of the Gaussian signal x of t equal to 1 by root 2 pi e power minus t square by 2. So this actually is a PDF. So x of t is a probability density function. So and hence what does it mean? This fellow's area is equal to 1. So let us keep that in mind. We will use this later. So I just wanted to hint you that this fellow's area is equal to 1. Okay. So question is we have to find the Fourier transform of this signal. Okay. But we have to use what? We have to use differentiation in time domain and differentiation in frequency domain property. Okay, so let us write down what is x of t. X of t is equal to 1 by root 2 pi e power minus t square by 2. Okay, right. So now what will I do is I differentiate this. So this implies d by dt of x of t is equal to how much here? So 1 by root 2 pi e power minus t square by 2 and again multiplied with minus t. Why? T square by 2 differentiation is 2t by 2, so 2 will get cancelled. Okay, this should be equal to how much? This should be equal to minus t by root 2 pi e power minus t square by 2. So clearly we can write this as what? So this implies d by dt of x of t would be equal to 1 by root 2 pi e power minus t square by 2 is how much? It is x of t. So you will get minus t times x of t. So you can write d by dt of x of t to be minus t times x of t. Now let us apply Fourier transform. Okay, so taking Fourier transform, what do we get? We get which property to the left hand side? Differentiation in time domain. So what do you get? J omega x of j omega would be equal to what is the right hand side here? That is differentiation in frequency domain. So t minus is there, I'll keep it. So tx of t will have what as Fourier transform? J times d by d omega of x of j omega. That would be the Fourier transform of tx of t. So j is common, he will get cancelled. So this implies d by d omega of x of j omega is equal to minus omega times x of j omega. So same equation we wrote in this form. Okay, so let us call this equation A and let us call this equation B. So clearly what is that you observe? You observe that equation A and B, correct? Equations A and B are same differential equations. Why? Why are they same differential equations here? How is this looking? Look at A. D by dt of x of t equal to minus tx of t. Look at B. D by d omega of x of j omega equal to minus omega x of j omega. So definitely they are same differential equations. So but where do they differ? So this implies what? So this implies they have similar solutions. Okay, so they have similar solution. So what do you mean by solution here? What do you mean by solution? Solution means what? Finding x of j omega. If you look at equation B, we have to find x of j omega. Then we say that whatever answer we get for x of j omega, that is the solution of equation B. Similarly, what is solution of A? It is finding x of t. So d by dt of x of t equal to minus t x of t is a differential equation. Finding x of t, we say that that is a solution of x of t. But we already know what is x of t. What is that? X of t is how much? It is 1 by root 2 pi e power minus t square by 2. So this signal will satisfy this differential equation. But what happens? Only the scaling factor differs. So what do I mean by that? For example, if I take some another signal x1 of t equal to, let us say root pi, some constant minus e power minus t square by 2. So this also satisfies. Okay, so this also satisfies the same differential equation A. So you can prove that d by dt of x1 of t would be again minus t x of t. So definitely what will happen to find a solution, we have to take care of the scaling factor. So theoretically there are infinite signals which will have same differential equation, but and what happens to the solution, they have not same solution but similar solution. So they differ in what, that's why note that here I used same, but one solution comes into the picture, I say similar solution. So this, what does this mean? This means the solutions differ in constant. Okay, so differ in constant. So what is the solution of equation A? What is the solution of equation A? That is x of t, which is 1 by root 2 pi e power minus t square by 2. So hence solution of B would be equal to how much here? Solution of B would be we should have similar solution, and hence you get x of j omega equal to e power minus omega square by 2. Previously in time domain we got e power minus t square. Here you will get e power minus omega square. But where do they differ? They differ in that scaling constant. Okay, that is c times e power minus omega square. So but what is c? How do you get c now? So everything boils down to finding the scaling factor c. So we know that, okay, so this implies c is nothing but, if you replace x of j omega with 0, what do you get? Correct? So, or I'll put like this. So what happens if I replace omega with 0 here? We get x of j0 would be equal to c. So what is c? C is just the Fourier transform of the signal at omega equal to 0. But x of j omega equal to how much? That is equal to integral minus infinity to infinity x of t e power minus j omega t dt. So this is a generic Fourier transform equation. So what will happen if I replace omega with 0 here? You will get integral minus infinity to infinity x of t dt, which is nothing but area of x of t. But in the beginning itself, what is that we have seen? We have seen that area of x of t is how much? 1. So what did we get? We got x of j0 to be equal to 1. So but what is x of j0 equal to? C. So this implies c is equal to 1. So if you substitute c with 1, x of j omega would be, hence x of j omega would be equal to e power minus omega square by 2. Okay, so that is the Fourier transform of Gaussian. But if you pay a little bit attention, you can see that this is also Gaussian. So let us summarize. So 1 by root 2 pi e power minus t square by 2 will have what as Fourier transform? E power minus omega square by 2 as the Fourier transform. So Gaussian signal will have itself as the Fourier transform except that scaling factor. Okay, so just to summarize in graphical notation, so Gaussian function, this is the standard normal function. Okay, so you get a Gaussian function like this. So the right hand side also, the Fourier transform will have a similar shape. A Fourier transform would be also Gaussian, but at omega equal to 0, that fellow is 1. At 0, this fellow is 1 by root 2 pi. Okay, yes, but if what is important, Gaussian will have itself as the Fourier transform. Which signal will have itself as a Fourier transform? One more example. If you remember, we have proved that a periodic impulse train also will have itself as the Fourier transform. Okay.